announcements. Okay, so let's continue. Just as a little reminder where we are, I emphasized that observed polarization signatures in stars can be quite complicated and might not look anything like the local Stokes parameters because we have surface integration. We are averaging over Stokes parameters coming from regions with very different field properties, different field strength, different field orientation. Now a few words about techniques which are commonly used, widely used in stellar spectropolarimetry. And there we have basically two problems. One problem is that the amplitudes of the signals that we are often dealing with are extremely small. So the fields themselves in typical stars, solar type stars, would be well below 1 kilogauss, so maybe global fields around Gauss or so, or 10 Gauss. So the amplitude of polarization is going to be small. And also there is this problem of cancellation of different field polarities, as I illustrated in the previous slide. So if we have spots with different field orientation, Stokes V parameters cancel each other and the total signal will become smaller usually. Until very recently, it was extremely difficult or even impossible to say anything about magnetic fields of stars similar to the Sun. And a real breakthrough was the invention of this least squares deconvolution method, which was first suggested in this article in the end of the 90s. So basically, this is the idea how to take advantage of the typical stellar observations, namely that in stellar spectropolarimetry, we usually are not really concerned about spatially resolving objects. We observe stars as unresolved points. And because of that, we can cover very wide spectral ranges. So typical stellar observations, unresolved spatially, just one point, but enormous coverage, say from 3,500 angstroms up to 1 micron. That would be typical coverage of modern cross-dispersed shell spectrum. So the idea is that in this spectrum, we have many, many lines. For solar type stars, thousands of lines. And the Stokes parameters in these lines are not completely dissimilar, right? In particular, if we use this weak field and weak line assumptions, as I demonstrated before the break, you remember that we basically had derivative of Stokes I scaled by the lambda factor in the field strength. And so, using this weak line and weak field approximations, it is possible to, in a very rough way, approximate the entire spectrum as simply as superposition of shifted and scaled mean profiles. So we have mean profile for Stokes I, we shift it to the position where a line should be, we scale it by some factor, and then sum together all lines contributing to a given wavelength. And this gives us the Stokes I spectrum. And the same approach for other Stokes parameters, Q, U, V. So this is formally how it can be written. So we have this Z are these mean Stokes profiles in I, V, and Q, and these W's are the weight factors. And one can, from weak field assumptions, one can understand that for Stokes I, this weight factor is simply the central depth of the line. For Stokes V, it's the product of the mean lambda factor, central wavelength, and the depth of the line. And for Q, for linear polarization, it is this capital G, sensitivity to linear polarization, times square of the wavelength times the line depth. Okay? And these formulas can also be equivalently written as a convolution. You can convolve this mean profile Z with the line pattern and get the spectrum, or it can be written as a matrix multiplication. So we have mean profile multiplied by this line pattern matrix M, which is built by knowing the central wavelength and knowing these weights. And this is the model of observed spectrum. Now, in reality, what we want to accomplish is, of course, something the opposite. We have usually a noisy spectrum, maybe looking something like this. This is the real observation of Stokes I and Stokes V. Stokes V here expanded by some factor of 3, I think. And you can see maybe there is some signal, but it's really hidden in the noise. So what we want to do is to invert the problem. Knowing M, this line pattern matrix, it just contains atomic data, and having observations and the error bars of observations, we want to get this mean Stokes signatures. And this is very easy to accomplish because this problem is actually a linear least squares problem. And for linear least squares problem, we can write down the explicit solution in this form of matrix inversion. So actually, what we have here is the cross correlation function, and here is the inverse of autocorrelation function. So this is how we can derive mean profile from the entire available spectral lines, from the thousands of angstroms, taking into account maybe 10,000 lines. And from this particular, of course, here I show not the entire spectrum, but small region. But taking all lines into account, one gets something like this. So now you see that we achieved a very great improvement in polarimetric sensitivity. Instead of this noisy signal, we get very well-defined Stokes V signature and Stokes I. So the typical gain, of course, depends a lot on how many lines we are able to use. The cooler the star, the more lines we are able to use. But typical numbers are between 10 and 40. So that means that if I have recorded spectrum with a signal to noise of 100, I applied this method, least squares deconvolution, and I get the mean profiles with perhaps signal to noise of 4,000, whatever. And this particular method, combined with some observational tricks that I'm going to explain later, allows to go down to polarimetric sensitivity 10 to the minus 5. So that's the kind of current state of the art in stellar spectropolarimetry, this level of sensitivity. And I should mention that least squares deconvolution is not the only multi-line approach. There are other approaches like principal component analysis, line addition, various improved versions of LSD. Now, the other question is, of course, okay, we've got this nice mean profiles, but how to interpret them? And this interpretation usually assumes that LSD profiles behave as real spectral lines for the mean parameters. So I can derive mean wavelength, I can derive mean lambda factor, and then model LSD profiles as if they represent real spectral line. And these are the tests trying to evaluate how this assumption is actually working. So with dots, I show LSD profiles derived from synthetic spectra, so from the spectra which have known magnetic field strength and orientation and so on. And then these solid lines plotted on top show the modeling of the LSD profile as a mean spectral line. And different curves correspond to different orientation of the magnetic field with respect to line of sight. And then columns here correspond to magnetic field strength going from 100 Gauss to 5 kilogauss. And these are Stokes I, V, and Q. And as you can see, there is an interval here, roughly between 0 and 1 or 2 kilogauss, and for Stokes IMV, where this assumption that LSD profile behaves as a real spectral line is a reasonable approximation. It doesn't work for a stronger field, and it doesn't work for Stokes Q. And, you should remember that most of the results that I'm going to show for the stars are based on using these mean line profiles. And there are certain limitations to using them. Right. There is a slightly different version of the multi-line technique that is used mostly for stars with global magnetic field. This approach is known as a so-called moment technique, and it was formulated originally by Gautier-Matisse in '89, and then there was a series of papers where he applied this to mainly intermediate mass magnetic stars. So it is possible, by assuming that lines are weak and assuming Milne-Eddington atmosphere, and without any limitations on the field strength, it is possible to establish relation between moments of Stokes profiles. So if we reformulate Stokes profiles in this way, so continuum minus Stokes profile divided by continuum in Stokes I, and then the moment of Stokes profile is this quantity multiplied by the difference in wavelength with respect to the center of gravity of Stokes I. So lambda I is the center of gravity of Stokes I, and in the power corresponding to the order of this moment. This is integrated over full extent of the line and normalized by equivalent width. So this is something derived from observation, okay? Moment of Stokes profile. And we can have moment of order 0, 1, 2, and 3, and so on for each of Stokes parameters. It is possible to establish relation between these quantities and these quantities, so surface moments of magnetic field. So these brackets here indicate integration over the surface. So Bz is the component of magnetic field along the line of sight, and this Bj is one of the two components that define the field projection perpendicular to the line of sight. So these formulas are completely general, but in reality, only 3 moments have been systematically used. Well, from first moment of Stokes V, one can establish what is known as mean longitudinal magnetic field. It is the component of the magnetic field parallel to the line of sight integrated over the surface of the star, Bz. And one can, from the second moment of Stokes V, so it is this formula with n equals 2, one can establish this quantity, average over of Bz, so component on the line of sight, times x, where x is the distance between the central meridian of the star and the point on the stellar surface. And this quantity is interesting because it was designed specifically to characterize situations like those that I've shown here, situations like this. This first moment of Stokes V is going to give you 0 if Stokes V is symmetric. But the second moment of Stokes V will be non-zero for this kind of profiles. So this is the purpose of this so-called crossover or asymmetry of longitudinal field. To be non-zero, this quantity is non-zero if there is a certain correlation between line of sight component of the field and Doppler shifts. For instance, if the redshifted part of the star has preferentially positive field and the blue shifted has negative field. Well, think about star with oblique dipolar field rotating, and you're looking at equator of the dipole. And then from the broadening from the second moment of Stokes I, essentially from the width of unpolarized spectral lines, one can establish quantity known as mean quadratic field, which is a sum of average of the square of the line of sight field and average of the square of field modulus. So these are the typical integral observables that are used in observations of stars with global fields, with stars with simple field topologies. You understand that if you have very intermittent field, that all these averages will be probably very close to 0. This is how moment technique is implemented in practice. So these moments are measured individually for each line, and then these correlation plots are produced, and the correlation is between the measurement, the moment, and certain atomic parameters. So in the case of longitudinal field, it's just the g times lambda, the lambda factor times lambda. So this is determination of longitudinal field. This is quadratic field. And of course, as I repeatedly emphasized, this method works only if we have regular field. If we have all spots all over the place, we are likely to get 0 low order moments. So the most general way to extract information about stellar magnetic field topologies is, of course, model line profiles themselves, or model mean profiles, these LSD profiles. And this is usually done in the context of what is known as Zeeman Doppler imaging. And the idea here is simple. The stars are usually rotating. So we see at different moments of time, we see different view of magnetic field. We have Zeeman effect, so we have, different strength of the field at different phases. We have Doppler effect, so the spots are carried, they appear on one side of the disk, and then they go to the center of the disk due to stellar rotation and disappear on the other side, and this corresponds to motion of their signatures within line profiles. And we have just geometrical projections. So as the star rotates, we see vectors from different aspect angles. And all these things together give us, in principle, enough information to recover two-dimensional map of vector magnetic field from time series of Stokes parameters. So this is illustration of rotating star with spots, magnetic spots, and the Stokes V signature. And spots here are different in the sense that I assumed radial, meridional, and azimuthal field for these spots. So the radial field is this one. This is meridional field, and the third one is azimuthal. And you can see that the signatures that you get from these different spots actually quite different. Especially, let's wait again for the azimuthal. For the radial field, the signature doesn't change sign and reaches maximum in the center of the disk. And for the azimuthal, look, it's large and then changes sign in the center, and then becomes large and then disappears. So the signatures of different field polarities in Stokes time-resolved Stokes spectra tell us something about field orientation. And this is something very basic that is used by Zeeman Doppler imaging. However, the problem of reconstructing magnetic field topology from time series observations is what is known as ill-posed or ill-conditioned problems, in the sense that there is infinite number of solutions satisfying a given observational set. So one usually introduces additional a priori assumption or regularization, as it is called. For instance, you can require the field to be smooth. So you add to the chi-square certain regularization function, and you try to find a solution which is the smoothest one satisfying observation. And it is interesting to note that this type of indirect imaging of stellar surfaces is probably the highest resolution method known to astronomy, because the resolution we get on the surface depends only on the spectral resolution of our data and the VCNI of the star. It does not depend on the distance to the star. So in practice, the resolution that we can achieve, for instance, using 8-10 meter telescopes, we can look at spotted stars at the other side of the galaxy. And to resolve such spots in a direct way with imaging, we will need telescopes of the size of solar systems, something like that. So it's quite impressive if you calculate these numbers. Now, this is rough idea how Zeeman Doppler imaging procedure is implemented, is carried out. So we are dividing stellar surface into a number of elements. And for each surface zone, we assume initial distribution of quantities, like initial map of free components of magnetic field. Well, usually we assume nothing, we assume zero field. And then sometimes the stars also have temperature spots, or chemical spots. So we need to assume some initial distribution of temperature and chemistry. And then for each surface zone, we calculate individual Stokes parameters. For each rotational phase, we integrate over the surface, and then we compare with observations. And then there is minimization algorithm that decides how much to change surface parameters to match observations. So there is this loop. And what we minimize is the sum of chi-square, the function describing the quality of the fit, plus this penalty function, regularization, that allows us to pick the smoothest, the simplest solution. And then we get something out, some maps. And in this process, as now you can understand why it is important for us to have very efficient methods of solving polarized radiative transfer equation. Because here we have to produce these Stokes parameters for each surface zone, for each rotational phase, and we have to do it many times because we also need to calculate derivatives. So we need to make steps, small steps in these parameters, calculating them, calculate the differences. So in practice, for a typical problem with rather small number of iterations, because we're usually trying to use efficient minimization algorithms, say 10 iterations, we would do this evaluation of Stokes parameters like 1 million times. So this is why efficient polarized radiative transfer methods are important. And this is an illustration of tests done for Zeeman Doppler imaging. So usually what we do, we assume certain distributions of, well, spots and magnetic field. So in this case, input maps are this, and this. And then we simulate observations. So we compute forward Stokes parameters, add noise, and then try to reconstruct back and compare these reconstructions with what we put in initially. And this is probably the sort of the best that we can achieve. So these are inversions using all 4 Stokes parameters. As you can see, very good reconstruction. In this case, I consider it global field, so something typical for stars more massive than the sun. Now, I also want to say a few words about instrumentation that we use for stellar magnetic field studies. And of course, there is very broad variety of things that one can do. And I roughly separated it into these categories. So photopolarimetry, some methodology that doesn't really rely on using very high spectral resolution. Then spectropolarimetry at different resolutions, and then Zeeman broadening measurements. So what is photopolarimetry? It is a technique when we try to measure signal, Stokes V signal, in the wings of broad lines, or in principle any lines. This technique was first used in the 70s, described in this paper. It was applied for stars with very strong lines of hydrogen. So what one does is observes the star with this kind of instrument. So light goes here, and in this particular implementation, they had electro-optical crystal. So a wave plate that changes its properties very fast according to some internal clock. And there is a beam splitter, so it splits the light into ordinary and extraordinary beams, and these beams are registered by photomultiplier tubes, and in between they put interference filters, so rather narrow filters, which in this case are centered on the wings of hydrogen lines, blue and red wing of H beta, for instance. And then this formula is used to derive magnetic field. I believe something very similar is used in producing full disk maps of the sun, focusing on the wings of some metal lines and deriving the line of sight component BZ from these measurements. Typically, what one can achieve for stars is around 50 Gauss precision error bars for the line of sight component BZ. And as I mentioned, of course, this works if we have broad lines with well-developed wings, so it's applicable to A, B, and O-type stars. There is a slightly different version of, well, a very different version of photopolarimetric method, and that is simply looking at the polarization in continuum, well, effectively in continuum, in broad wavelength regions. So we are not using any special filters, just regular Johnson filters, for instance. And what we are looking for is the signal which appears in the Stokes Q and U spectrum due to differential intensification of pi and sigma components. So to get this net linear polarization signal, we need to have strong lines and fairly strong field. And still this is kind of precision that needs to be obtained in order to see this broadband linear polarization. So it's polarization coming from individual spectral lines, from differential intensification of Zeeman components in them. And it is limited to intermediate mass stars with strong fields. And we get this kind of curves. So this is a curve showing measurements as a function of rotational phase. Sometimes, so this is Q, this is U, or sometimes measurements are plotted as this looks, U versus Q. Now going a bit higher in this ranking of methods based on resolution. Low resolution, it is kind of important because that's the only type of measurement we can do at the largest telescopes nowadays. So large telescopes have only low resolution spectropolarimeters suitable for stellar observations. In particular, this instrument FORCE at the VLT is used very widely for stellar research, for stellar magnetic field research. This is kind of spectra one gets from FORCE. So this is Stokes I and Stokes V, and you see all these signatures in Stokes V. These signatures are not noise. This is unresolved in case of metal lines, unresolved in case of hydrogen lines, partially resolved Stokes V signatures for a strongly magnetic star. And what one can do, one can again rely on the weak field approximation. So I'm again writing this formula, weak field approximation, and establish the line of sight, mean line of sight component, longitudinal field, by comparing V divided by I to the derivative of I. And this linear correlation is illustrated here. So the presence of correlation between these quantities, V and derivative of I, is the signature of the presence of the field. So in this case, it's a fairly strong field, several kilogauss. But this technique has been used to measure fields down to maybe 20 or 30 Gauss. And this is, again, this is the only method if you want to look at very faint stars located far away. There is also a range of medium resolution spectropolarimeters operating at 2-meter telescopes and larger telescopes. And in particular, these medium resolution spectra are used for the moment technique analysis. In my definition, medium resolution is somewhere around lambda divided by delta lambda is between 5 and 20,000. That's what I call medium resolution in this context. And what one can do, one can say that what is really measured on the detector is the I plus V and I minus V, so-called left-hand and right-hand polarized spectra, RCP and LCP sometimes they're called. These two spectra are plotted here, and well, the resolution is not sufficient to see it clearly, but one is shifted slightly with respect to another. And this shift is proportional to the lambda squared magnetic field and the mean lambda factor. So what one does is measuring the center of gravity in one of these spectra and subtracting center of gravity in another spectrum and then deriving the field. This part of the equation is actually mathematically fully equivalent to computing first moment of Stokes V. So you could have just derive the same thing by integrating this signature Stokes V. So this is a typical medium resolution spectrum of magnetic star from, I think it's from Russian 6-meter telescope, and this is from 2-meter telescope in Canada, so you can clearly see Stokes V signature in the core of primal line. And again, the same formula can be used to derive longitudinal field. And then going further in this resolution scale, high resolution, the most sophisticated techniques for stellar spectropolarimetry is resolution higher than 30,000. Going up now to, I think, 110, 115, this is what is possible with HARPS polarimeter. And with this technique, what we can achieve is really precision in longitudinal field below 1 Gauss and polarimetric sensitivity 10 to the minus 5 when it is combined with a multi-line approach. And here I list a few instruments of this kind that were used or currently being used for stellar magnetometry. So these two musicals at 2-meter TBL at Pic du Midi is decommissioned now. This is also decommissioned, but it has been used for a lot of observing proposals here in La Palma, Sofin at Nordic Optical Telescope, and these three are the currently most widely used, the Narval at Pic du Midi, Espadons at CFHT, and HARPS polarimeter at ISO 3.6 meter telescope. And these images illustrate roughly how the raw data from such high resolution spectropolarimeter would look like. So what is shown here is the image where we see a shell spectra. So this is this wide spectral coverage, and the spectrum is sliced into orders. And this is a zoom picture. I think this is spectrum of the star. This is spectrum of comparison lamp, some sort of amalgam. And this is zoom of the two images, and you can see that orders are doubled. So what we are recording here is again this I minus V and I plus V. So the two spectra simultaneously recorded on the detector. All right, but this is not all of it. All of it. Until middle of 90s, people would approach calculating Stokes parameters from observations in a simple-minded way. So we have one spectrum, which is I plus V, another spectrum, which is I minus V, and we compute V as a difference between the two. And this is the typical, very simple spectropolarimeter, actually. It's the real HARPS spectropolarimeter. So we have rotating retarder plate. For Stokes V measurements, we're using quarter wave plate. We have a beam splitter, and we feed the resulting two beams into fibers, and then spectrograph produces us this image that I've shown on the previous slide. Okay, so remember that in order to measure very low magnetic fields, we really need to achieve very high precision differential measurement of these two spectra. For instance, this is the figure that you can easily find, that 1 Gauss, and this is our aim, 1 Gauss, is corresponding to something of the order of 2 meters per second in velocity shift. So we are in the regime of finding low mass planets here. And okay, we have these two spectra, and in the ideal world, the difference gives us Stokes V. But in reality, things are much more complicated. We are projecting this spectrum different parts of the detector, so they are affected by all kinds of instrumental. Yes? Well, or for massive planets far away from there. Yes. Yes. No, it's not so much simple. I mean, if you, for instance, do repeated measurements with I don't know, UV spectrometer at the VLT, 8 meter VLT, you will find that the velocity changes by 1 kilometer per second during the night. So achieving 1 meter per second short-term stability is not trivial at all. Yes? Yeah. Yes, but still what I'm trying to say, since our detectors are not perfect, and you have seen maybe on this slide, you see this bright column, this typical imperfection of CCD detector, and there are all kinds of distortions like interference, fringing pattern, which affects these different beams in different way, and these fibers may have different efficiency. Okay. And all kinds of things may happen. So in reality, if we compute this difference directly, we get maybe in the best case 10 to the minus 3. So this is an illustration. I add to one of these beams, one of the spectra, I add some distortion. In this case, just a sinusoidal variation. And sure, in the spectra obtained with a simple formula, we get this distortion. And we can easily get spurious polarization if we are not able, for instance, to establish the relative wavelength scales of this spectra with high precision. So what is done, this is an illustration, for instance, of this problem of wavelength calibration. I made an arrow in assigning wavelength to this IR relative to IL, and then I can even switch the sign of the signature, Stokes V signature, relative to the true one. Now, what is done is this very simple trick. I think it's first been introduced by Meyer Simmel in the beginning of 90s. We rotate this quarter wave plate by, in the case of Stokes V, by 90 degrees. And then what this does, it exchanges the sense of polarization. So if we had IR going here and IL here, then after rotation it would be the opposite. So instead of one observation of two beams, we have two observations of two beams. So we have 4 spectra. And then we derive the spectra using this formula. Okay? And what this does, it effectively removes all systematic effects due to the things happening after polarimetry, due to detector imperfections, due to difference in sensitivity between fibers, and so on. Using this technique, it's in fact not even necessary to obtain flat fields. It's not even necessary to calibrate detectors. It's enough for detectors to be stable. And this very method, which is known as beam exchange technique, is, when combined, of course, with multi-line methods, is the method that gave 10 to the minus 5 precision in stellar spectropolarimetry. So remember, we are obtaining not a single exposure with two beams, but at least 2. And if we obtain 4 spectra, rotating, say, having orientation 0, 90, 90, and then 0 again, we have certain redundancy, so we can compute actually not only polarization, but we can compute so-called null spectrum, the spectrum which is supposed to be to show just noise, and if there are some signatures in null spectrum, this is an indication of problems happening before polarimeter. Some spurious polarization caused maybe by some components up there in the stream. Yeah. This does not affect this, because in this setup, in this experimental setup, transparency variation amounts to nothing but change of the overall level of intensity. And you see I'm normalizing here. I have the ratio, right? The difference divided by the sum. So if my second exposure has a difference in the level of counts of photons, this will be removed. Of course, this series of exposures need to be obtained fast enough so that the star itself doesn't change. That's for sure. If the star is doing something, we should obtain observations quickly enough. So we are not affected by seeing variations in stellar spectropolarimetry at all. All right, and here I actually illustrate. I put in all these weird distortions, flat fielding variations. Actually, I put in also these different levels of the spectra corresponding to seeing variations, maybe, and all these distortions. And then at the end, I get out still perfect Stokes V spectrum using this formula. So this is something that is now routinely used in stellar spectropolarimetry and seems to be a very efficient methodology. And all these things implemented allow to get nice spectra and allow to get also reasonable agreement between different instruments. So this is illustration of the spectra taken with this instrument, Espadons, and this instrument, Harpspol. And they have different resolutions. So Harpspol is about 115,000, and Espadons is 65,000. So the red is Espadons, and blue is Harpspol. And this is spectra in all four Stokes parameters for a star, intermediate mass star with very strong field and extremely long rotation period, so some decades. So even spectra like this taken a few months apart should be identical. And, well, they are identical to the precision of the measurements. And then finally, another technique which, as you will see, is used for some types of stars is measurement of the field modulus. So extracting information about the splitting of spectral lines from Stokes I. And for that, of course, one also wants to use very high resolution spectra in order to separate Zeeman broadening from all other effects, from rotational broadening, from intrinsic Doppler broadening due to thermal motions and so on. Well, 10 to the 5 is an ideal world that what we want to use. And important notice that this technique is sensitive to much stronger fields. In order to see noticeable additional Zeeman broadening in Stokes I, you need half a kilogauss or more than kilogauss. And, well, it's based on this formula that the separation of sigma components in a triplet line with respect to phi component is given by this. So again, effective lambda factor gives sensitivity of the line, and then this is the average of the field modulus over the surface of the star, and you see that the splitting grows with lambda squared. So the further you go into the red, the more sensitive you become to extracting information about field modulus. And this is a couple of examples of extracting information, measuring field modulus. And in this case, it's the optical spectra, and field is not very strong, around 1 kilogauss. And what is compared here is observations with dots and synthetic spectra for lines with different magnetic sensitivity, different G. So this is G0, and these lines have G3. And the solid line is the model spectrum with magnetic field, this magnetic field, and dashed line is the model spectrum without. And you can see that we need magnetic field to match profiles of lines with different magnetic sensitivity. If the field is strong enough, or if we're observing very far in the red, yes? Yes, only intensity. No, these are realized. These are realized. So LSD doesn't work on this kind of method, because in a weak line approximation there is no effect on Stokes I at all. You can't formulate LSD for Stokes I. And in this case the field is a bit stronger, and these authors have also looked at magnetic star using CRIRIS, so using a high resolution ESO spectrometer working in the near infrared in the around 1.5 microns. In this case they have two lines and there is clearly splitting, and you more or less can directly establish what is the B by measuring separation of this component with respect to another component. So this is what I wanted to say about the methodology and the basics, and now I'm going to describe going to part 2, describing observations of magnetic fields in stars all across Hertzsprung-Russell diagram. And in particular, I have identified these classes of stars for which a lot of research has been done recently. So solid type stars, intermediate mass stars, massive, low mass, young and evolved. And of course, I don't have infinite amount of time, so there are some aspects, some classes of stars which I'm not able to cover in these lectures, and I apologize for that. And this is also the order that I will proceed. So today I hopefully will cover solid type stars. So the way I will approach each type of stars is roughly outlined here. I will say a few words about which of the methods that I have already mentioned before in the first part, which of the methods is the most efficient for this particular object, and what are the recent observational results, and relate these observational results to outstanding theoretical questions. And in this overview, I decided not to spend too much time on the historical overview, so I will not tell who were the first who observed these stars and so on. So I will start with solid type stars, and here I define solid type in the broadest sense of this word. So something with a temperature, maybe a spectral class between F and maybe late K. So stars which are sufficiently cool to have large surface convection zones, and maybe close to the main sequence, but maybe also slightly evolved, with giants and subgiants, and in this range of masses. So here I'm plotting the theoretical HR diagram. I will use these plots to identify regions which I'm considering. So as an overview of the basic properties of these stars, I can say the following. That, we assume that all these stars should have magnetic field at some level. They have convective envelopes, so some magnetic field should be generated. They typically have relatively weak field, unless we look inside very small cool spots. So typical fields that we should expect for these stars is well below kilogauss. Fields evolve, and that's important consideration. If we want to observe, for instance, to use Doppler imaging, that means we have to acquire our data set looking at star at different rotational phases fast enough so that the star doesn't have time to change its field. And fields are complex, so intermittent. There are all these kinds of dynamo theories describing how field can be generated. In particular, for these stars, there is a question whether or not magnetic field is primarily generated by the shear at the base of convection zone, so-called tachocline dynamo, or maybe by more distributed dynamo process in the bulk of convection zone. There is cyclic behavior of the magnetic field, known from the sun, of course, and there is a certain correlation of magnetic activity with age. Younger stars tend to be more active, and with rotation, faster rotating stars tend to show signatures of magnetic field more often. What is really important to emphasize in the context of this series of lectures is that for these stars, direct detections of the fields have been extremely difficult until very recently, practically non-existent until recently. So the entire field, for many decades, relied on what is known as proxy diagnostics of magnetic activity, so magnetic activity in quotes. So actually, if you try to search, for instance, ADS papers with magnetic activity of stars in the title or in the abstract, you get 99% of papers looking at proxy indicators, and only 1% of papers would actually go and measure magnetic field using one of the techniques I mentioned. So these proxies are secondary indicators of the presence of the field. And at different levels in the stellar atmosphere, we see different manifestations. Deep down magnetic field for solid type stars prevents convection energy transport, so it is responsible for these dark spots. And when we integrate over the disk of the star with the spots and the star is rotating, you understand that the brightness of the star is changing quite a lot, or maybe not so much, depending on how large are these spots. So photometric variability of cool stars is an indirect evidence that magnetic fields must be present on its surface. And we have this beautiful data sets coming now from space experiments such as Kepler, Corot, and a Canadian Moss satellite that give us very precise and long-term measurements of light curves of the stars. Then if we go higher, above photosphere, we have chromosphere, and their magnetic field is responsible for additional heating. And we are seeing the emission in calcium H and K. So this picture is supposed to show photospheric level with dark spots. This picture is the image in the core of calcium line. So you see this brightening. And then if we go even higher, we see X-ray emission in the corona, so the coronal loops. And these things, these proxies, show a correlation with the number of sunspots. So the cyclic behavior is as illustrated here for calcium H and K emission. And as I mentioned, there is, if we look now for stars, there is nice correlation between age and rotation and this proxies, magnetic activity. So this is the plot, I believe, Phil has already shown the plot from the very same paper. So it's a really influential paper that plotted emission in calcium H and K as a function of rotational period of the star. So the shorter rotation, higher is the emission. And this is a similar plot, but for the X-ray, X-ray luminosity. And in fact, if one plots proxy of magnetic field as a function of rotation period divided by convective turnover time scale, then one gets what is known as Rossby numbers, and this plot becomes much tighter. So we have sort of linear increase in this log-log plot and then saturation regime. So presumably this tells us a lot about magnetism, dynamos, and so on, and there have been a lot of speculations about what this means. But the truth is, we have no idea what this means for magnetic field strength and topology. We have no idea what is the strength difference, for instance, for stars here and here, and is there or not any difference in topology for stars in the saturated branch and in this linear branch. So since the end of 90s, we are more moving into the regime where we try actually to measure the field itself rather than rely on these proxy indicators. And such measurements have been first performed in this paper in 97. This paper in 92 was maybe the only that could demonstrate signatures, Stokes V signatures in individual spectral lines. So, well, you see some noisy signature in line with large lambda factor 2, and the lack of signature in line with much smaller magnetic sensitivity. And this doesn't look very impressive. And still, this is signal to noise of like 600-700. That's what they obtained. And they looked at the most active star in the solar vicinity. So this is what is possible to do looking at individual spectral lines. Then they invented least squares deconvolution, multi-line technique, and suddenly it became much easier to detect magnetic fields. And here is this little selection from this paper of different stars. So this is a young binary star, so you see actually two components in Stokes I, but only one component seems to produce at this particular rotation phase observable signature. And this star is actually the same as here. Also nice signature, and again signature here. And you see that in many cases, like here, signatures are rather complex. So by computing a simple first order moment, you don't gain much. You probably obtain something that is close to zero. You really need to work at the level of line profile analysis for these stars. And this is perhaps the most extreme example. So what is plotted here is again Stokes V, but it is stacked. So different observations obtained at different times correspond to horizontal lines here. And you see some evolution, some regular evolution. So magnetic spots appear, move across the disk, and disappear. So this is the young, very rapidly rotating solar-type star AB Dor. And these detections all correspond to extremely active stars, stars which show a lot of cool spots, huge variation in brightness. Certainly, I bundle them together with Sun, but they are quite different from the Sun concerning the level of magnetic activity. Now, with more modern instruments like Harpsball or like Espadons, it's now possible to detect magnetic field signatures in stars which are moderately active. Like, for instance, these are two observations obtained for Epsilon Eridani, so nearby K-dwarf star with a little bit enhanced level of activity. And okay, what is plotted here is Stokes I LSD profile, Stokes V LSD profile at two different observing nights, and it is scaled, it is enhanced by a factor of 200 relative to Stokes I. And the top spectrum, which doesn't show anything, is this diagnostic null profile that, as I mentioned, we usually obtain as a byproduct of getting this sequence of spectropolarimetric observations. So the flatness of Stokes of null, a diagnostic null spectrum, is telling us that there are no spurious polarization signatures. And then the plot here is observation of alpha Cna, where we don't detect magnetic field. And you see that here Stokes V and null spectrum are multiplied by factor of 1000. And actually this spectrum is where one of those observations where we reach 10 to the minus 5 precision. And okay, if I would overplot expected Stokes V signatures for different line of sight magnetic fields, they would look like this. So this sequence of curves correspond to line of sight, mean line of sight field from 0.1 to 1 Gauss. So this is the lowest is 0.1, this intermediate is half Gauss, and the top curve is 1 Gauss. 1 Gauss is roughly the global line of sight magnetic field of the Sun at the maximum of solar activity. So we can say, and this is confirmed also from analysis of proxies, that this particular star, it's a kind of old star, inactive star. This star seems to generate magnetic field less efficiently compared to the Sun. Okay, so what can we do with this Stokes mean Stokes signatures, except of looking at them? There is a fairly rigorous false alarm probability detection principle that usually applied. So those signatures which I've shown you, they were very clear. But very often we have something at the level of noise and we are not sure is it a detection or not. So in that case, we're using this formula. So gamma is, this is incomplete gamma function. This is mu is number of degrees of freedom. It's just number of points in LSD profile. And this is chi-square, so it's the square of the signal divided by the error bars. So this gives us probability of detection of the signature, and 10 to the minus 5 is what we usually require to say that detection is definite. And then, of course, one can, from Stokes V, calculate from first moment, calculate line of sight field, again, longitudinal field. In the case of LSD, usually this formula is used. So integral of Stokes V multiplied by velocity normalized to equivalent width of the line, scaled by some factor. And this is example from the full set of observations of Epsilon Eridani. This is the curve of longitudinal magnetic field that we have obtained for an observing run which followed this star over some 12 days, and it's close to the rotation period of Epsilon Eridani. And, well, the precision here is 0.1 Gauss, and the amplitude of the BZ variation is around plus minus 5 Gauss. So this is kind of the best that one can do for very bright star with sharp lines with a lot of, with very dense spectrum. And also, since the star is rotating not very fast, these Stokes V profiles look quite simple, and then measuring longitudinal field, measuring first moment is useful. But if stars have faster rotation, more complex Stokes V profiles, it's becoming not so useful to measure longitudinal field, and this is example of when this formula doesn't give us any insight, is correlation, or rather the lack of such. This is longitudinal field, and this is the amplitude of the Stokes V signature. So the star has lots of ups and downs in Stokes V. So large amplitude does not necessarily correspond to large longitudinal field. So here, days. Yeah, the star has field which is not axisymmetric. It rotates and shows us different projections of this field. Yes, quite naturally explained, I think. I mean, we will see many more of such examples for massive stars which have oblique dipolar fields. This is perhaps the most comprehensive magnetic field survey which sort of got snapshot observations in Stokes V and tried to correlate them with the proxies, with emission in the calcimation K, and well, you see kind of loose correlation in the sense that there is this upper envelope. The larger is the emission, the likelier it is to find a very strong field, but still, sometimes stars with very large emission give you not very large BZ. And there is also some loose correlation with the of BZ with age, so it's more probable to find strong line of sight field in younger stars. Yes. No. We just measure average line of sight component. And yeah. Yes. Mm-hmm. yeah, of course, ideally for each of these stars, we should do full mapping of magnetic field and correlate resulting quantities with RH and K. That's what. Yeah, I'm. Yeah, that would be my interpretation. So. Anyway, so what, of course, what we really want to do is to perform imaging, the Zeeman Doppler imaging of these targets, and as you understand, this is really massive amount of observing time that has to be invested in order to get suitable observational data sets. So this kind of work is done for a small number of stars, maybe 50 up to now. I will present a few examples of these Zeeman Doppler imaging maps, but before I go into that, I'd like to emphasize the two, first of all, I'd like to emphasize two methods that are used to parameterize the maps. So one can use direct parameterization, just specify three components of the magnetic field, radial, meridional, and azimuthal, as a function of angles of the angular coordinates on the surface of the star, or what one can do, and this is done in most studies, is to describe magnetic field as a superposition of harmonic components. And in that case, so these are the formulas, in that case what is being searched for is these harmonic components alpha, beta, and gamma, which describe poloidal and toroidal magnetic fields, and they are usually constrained by this penalty function. So the sums of squares of these coefficients should be minimized. And just to give you graphical illustration of what is meant by poloidal and toroidal fields, for one particular combination of L and M, angular degree and azimuthal number of spherical harmonics, I plotted distribution, surface distribution of the field, and the background image corresponds to the strength, and there is also vectors corresponding to field orientation. So for the poloidal component, we have radial field, which corresponds to alpha coefficients. We have horizontal component, also corresponding to beta coefficients, and we have toroidal component. And for toroidal component, magnetic field lines are going like this. So what is important to realize that toroidal field in these inversions is maybe not the same toroidal field as in the context of hostess, for instance, lectures. I noticed that theoreticians tend to call toroidal field, when they say toroidal field, they actually mean azimuthal component of the field. But here it's a completely different thing. So every spherical harmonic has, in principle, toroidal field. And then, okay, we plug this machinery and do inversions, and these are typical maps that one can get. In particular, these three stars were studied very, very much with time series of maps even, and these are very active stars, stars which rotate fast, either because they are young, so they have not lost yet their angular momentum, or because the stars are in the binary systems, so their rotation is locked with the orbital motion, so they retain very fast rotation, and this fast rotation somehow enhances production of magnetic field. So what is plotted here in these four pictures is the spot distribution, so the darker regions correspond to presumably to cooler spots. Although in this study it was not the temperature that was reconstructed, it was just the brightness. And then these are the three components of the magnetic field, so radial, azimuthal, and meridional field. And you might not see exactly what is the scale here. It goes up to 1 kilogauss, +1, -1. So that's the strongest field that one can expect in the most active stars with parameters not very far from the sun, 1 kilogauss. So what one can say, I mean, there is no clear correlation, first of all, between this dark region where presumably cool spots are and magnetic features. Well, maybe there is some, but not one-to-one. And what is really puzzling, and it was discovered as part of this first Doppler imaging studies, is that very often we get huge azimuthal field. So sometimes magnetic field is entirely, magnetic maps are entirely dominated by these rings of azimuthal field. And as you might remember from previous part, signature of azimuthal field in Stokes V is quite different from signature of radial and meridional field. So we are fairly certain that we can disentangle this component from these two. So these two actually kind of difficult to separate. But the azimuthal field is well separated. So nothing like that was predicted by models of magnetic field generation extrapolated from the sun. And then more recently, there have been also studies of stars with not so large magnetic field strength, closer to solar parameters. And for instance, in some studies it was observed that stars changed their polarity, and these were the first observations of stellar magnetic cycles, not magnetic proxies cycles, but real magnetic field cycles. And one of the first stars which was observed to change polarity was Tau Boo, F-type star with close-in planet, and you see radial, azimuthal, and meridional fields, but now the projection is pole-on projection. So you see kind of the star from the pole, and this thick line corresponds to the equator. And, well, the authors say that between these two observing sets, the predominant field polarity has changed. And indeed, I mean, there are more maps published in their paper, and maps shortly before and after they look quite similar to these ones. So the star changes polarity. During this moment, nothing happens with proxies. Okay? Proxy indicators stay the same. So these cycles that were observed, magnetic cycles observed for Tau Boo, for Xi Boo, and a couple of other stars, they have no correlation whatsoever with the activity as traced by the long-term changes of proxies. We don't understand what's going on, really. And I can even rotate them. No, but wait. If we look at the sun as a star, what happens with the global magnetic field of the sun during the cycle? Does the field sign change? I think it does. Yes. So we really need, when you know, having these kind of discussions, we really need to think sun as a star. Well, it's the question what we're really calling the magnetic cycle. Is it cycle of proxies or cycles that are revealed by these polarity reversals? Anyway, this is ongoing field of research, and there are just very few of such observations available with stars reversing their fields. Yeah? Not that I'm aware of. Of course they show flares, but not really cyclic. Maybe one should also clarify one thing that has also been observed from the proxy side, that the more active is the star, especially if stars are appearing on this saturated part of some proxy versus rotation period, there is a tendency for such stars not to show very well-defined cycles. Okay, so cyclic behavior is something more typical for stars with activity levels similar to the Sun, or maybe a little bit more active. Okay, this is another example of observations, ZDI maps that have been carried out by us using observations from NOT spectropolarimeter, and in this case we really followed one of the most active star, Ia Pegasi, over a long time scale, and we reconstructed magnetic field distributions and spot maps, and this is some kind of summary of what the stellar magnetic field was doing between. So the first observation is 2004, and the last one is 2010, I believe. So this is the 7-year span. So what is shown here on top is the overall energy of magnetic field. So it seems to have been going down. And different colors here correspond simply to different quality of the data sets. So the blue ones are the best quality, the best rotational phase coverage. The red is acceptable quality, and black is bad. And we only had 1 or 2 or 3 spectra. So it seems to have been, the field has been decaying. But if one looks at the relative energy in the poloidal and toroidal components, what is seen is some kind of oscillation. So the toroidal component energy is shown with open symbols, and poloidal with field symbols. So there is sort of oscillation here. And also oscillation is seen if one compares energies in axisymmetric and non-axisymmetric components of the field. And all this is sort of awaiting theoretical interpretation. Now, this basically repeats what I said. Now, going to a slightly different aspect, we know that for the Sun, from theories, generation of magnetic field is closely related to what is known as differential rotation. So what do we know about differential rotation for stars other than the Sun? Well, for what concerns the radial dependence of rotation, internal differential rotation, that can be measured using astroseismology for certain kinds of stars, but there is no overlap so far between these active stars with magnetic maps and astroseismology. Too bad. I don't know why. So we can't really say much about what's going on in stellar interior. But in fact, by tracing spots and by including differential rotation in the inversion process as additional parameter, we can figure out what is the surface differential rotation, how fast, for instance, equator rotates relative to the pole. And this is an example of such determination. So what is done here is parameterizing differential rotation in this way, inspired by the Sun. So we have equatorial rotation speed, and we have this delta omega, the difference in rotation rate between equator and pole, and this sinus square, sinus of latitude. And then for different values, for the grid of equatorial omega and delta omega, so there's this grid, they repeated inversions, and mapped the chi-square surface. So presumably this point corresponds to the best fit combination of rotation, equatorial rotation, and the delta omega. So this corresponds to detection of differential rotation. And this is a fairly large differential rotation. For other stars, smaller values have been measured. And what is interesting to note that very often one sees a difference in the differential rotation inferred from modeling Stokes I, so inferred from modeling cool spots, and values inferred from modeling magnetic field. So this difference. Why is that? It's not clear at all. Furthermore, there have been observations suggesting that there is a temporal variation of differential rotation. So the same star observed with the same people with the same technique and reconstructing maps of surfaces and deriving differential rotation in different years, they got sort of different values. Maybe that is related somehow to long-term magnetic cycle. Again, it's not really explained at the moment. Still puzzling. With the most up-to-date techniques and the best instruments, it's now possible to see magnetic field signatures of stars very similar to the Sun, even solar analogs, solar twins. So one of such stars is well known, 18 Scorpion, star with parameters extremely similar to the Sun. And these are the magnetic maps reconstructed from Stokes V. Obviously, the star is not so fast rotating, so the resolution that one can get on the surface is not particularly impressive. We don't see small spots, we see global field, but nevertheless, there is some field, and the scale here is 5 Gauss, from minus to plus 5 Gauss. And this study, which studied 18 Scorpion, has also looked at other stars with temperature exactly like the Sun, but with different rotation rates, with different rotation periods. And what they have discovered is that there is a very strong, very obvious relation between energy in the poloidal field and toroidal field versus rotation rate. So for the stars which are rotating, which have long rotation periods similar to the Sun, poloidal field dominates. So the energy in the poloidal field is this red line. So poloidal field dominates compared to toroidal field. But as the period decreases, so as the star rotates more rapidly, and in particular if rotation period is below some 15 days, the dominant field component changes energetically. So the toroidal field starts to be dominant. So from the point of view of these maps, it simply means that we are getting stronger field in horizontal maps relative to the radial field. Okay, so this is what happens even if we take a very, very small part of the HR diagram, looking at the stars which are extremely similar to the Sun, and change one parameter, rotation speed. So nothing like that was apparent from their proxies or whatever. Yes? Yes, you probably can. I don't know either. Yeah. Well, not me, but in this field was obtained. So, yes, we people, yes. So this is one illustration of how things can change rather obviously, and I would say dramatically, even in the vicinity of solar parameters, if we are reconstructing magnetic field itself. No idea. No. Mhm. Yeah, maybe, but mm. Mm. Well, observationally, what you're suggesting is quite challenging, because for these stars, we simply don't see spots. Maybe. So for these stars, if we would have Kepler-like light curves, maybe we could say something. Yeah. Okay. But these nice maps, of course, have a lot of limitations, and I should very clearly emphasize that one needs to have some healthy skepticism, and really keep in mind that these are inversions of ill-posed nature, and penalty functions and details of these inversions can very seriously affect the results. So one very serious limitation that was affecting essentially, well, 90–95% of all published maps is that in these maps, when reconstructing Stokes a magnetic field from Stokes V data, people simply ignored the presence of cool spots. So they treated formation of spectral lines using simplified formulas as if these lines are forming in unspotted photosphere. And maybe this is the result, this is exactly the reason why there is no clear correlation between cool features and magnetic field features. So what I'm showing here is perhaps one of the most extreme examples of disagreements of magnetic imaging for the same star. So this star, it's weak line T-Tauri star, so young star, rapidly rotating, fairly strong field. One study which has not taken into account temperature spots when doing magnetic field reconstruction, and another study did the two simultaneously, taking into account temperature and homogeneities when mapping the field. So this is the temperature distribution. It is dominated by large cool spot, and this is the magnetic field they got. And this is supposed to be the same star. Well, projection is not the same. This is polar projection. These are spherical maps. But these inversions are based on the data sets acquired within some weeks from each other, using the same instrument. Independent studies. And completely different view of magnetic field. Here it's mostly radially, dominated by radial component, very clearly correlated with polar spot. Here it's mostly azimuthal and more patchy. So this is what these limitations need to be kept in mind. And of course, the major limitation that persists for all these analyses of cool stars, solar type stars, is that observational data that we're using in studying these stars is limited to only unpolarized spectra, Stokes I and Stokes V. And that is simply because it is even a challenge to detect Stokes V, and Stokes Q and U linear polarization signatures, they are roughly one order of magnitude weaker. And when we're using only Stokes V observations, we are losing some information about magnetic field, in particular about the transversal magnetic field components. And what is well known for people who are doing Zeeman Doppler imaging, that with IV mapping, when we reconstruct all three components together, it is often difficult to distinguish between radial and meridional field components. And these examples of reconstructions from simulated data done by Lisa illustrate this problem. So these are the true magnetic field and temperature distributions. Well, it doesn't have any temperature spots in this case. And these are reconstructions. And these are reconstructions in the idealized case, when we even didn't add random noise to observations. Okay? It turns out that the code happily interprets Stokes V profiles not as a purely radial field, but it sort of moves field from radial to meridional component. Now, if we would add Q and U, we obtain much better constraint on transversal field, and we can really disentangle meridional and radial field, and can even detect field within this cool spot. So this is inversion illustrated below. These are inversions from simulated data. Can we really detect cool stars in all four Stokes parameters? Until recently, it wasn't even tried, and in these couple of papers, we actually tried and succeeded to do it for the most active star. So it's the same star, II Pegasi, that was showing up in previous slides. A very prominent bright star with kilogauss magnetic field. So what you see here is Stokes I. It looks so strange because it's a binary star. So it's a giant star locked with a dwarf star. So the dwarf star is this one, and this is a giant star. The profile is very much distorted because we get these cool spot signatures. Okay, this is a star, well, it's actually another star, but belonging to the same class, so called RSCVN stars, so binary stars locked where the rotation period is equal to orbital period, and the primary is fast rotating. So you see signatures in V and in Q and U, and for the other star, for II Pegasi, with a different instrument, so this is Harpsball, this is Espadons. This is what we obtained, and well, there is a clear detection of signatures in Q and U profiles, and we hope that this will lead to much better understanding of limitations of the inversions. So we are going to compare what happens if we get the maps from only V and from all four Stokes parameters. Well, not V, but Lisa is going to do. Okay, so what about theory? Can we say anything, what all these observations are telling us, and are there theories that are able to explain observations or to sort of connect observations with sort of basic properties of the stellar interior? And well, not really, I would say. There are good attempts, good tries, but we are very, very far from having anything simulated that resembles these real Zeeman Doppler imaging maps. So this is kind of overview of what is happening on theoretical front, so to speak. And it all starts, as we hear all the time, by applying solar paradigm. So there is some phenomenon observed for the sun, and we are trying to simulate what happens in stars with parameters different from the sun by enhancing this phenomenon. For example, in this particular study, what is done is that this author, Carl Schreiber, studies emergence of bipolar regions. And he has some model that describes more or less the behavior of magnetic field for the sun. And then he assumes that if the star rotates more rapidly, what happens is simply more bipolar regions emerge on the surface. So this is kind of faster rotating sun. But, okay, here he doesn't even have horizontal field. This is entirely radial bipolar regions. So this is completely different from what we observe in reality. We observe toroidal field very often, these rings of azimuthal field. So this doesn't work. Solar paradigm doesn't work. A number of more recent studies tried to really approach this problem with direct numerical simulations. So putting star, well, either using some box in the star approach, so computational domain covers some part of the star, or putting the entire star in a box, so the full star is included. And of course, in such computations, it's very difficult to capture the full range of, say, density variations, and you can't achieve the same Reynolds numbers as in the reality. But there are certain interesting results. In particular, this is simulation coming from the group of Brown et al., but also Sacha Brun in France is using the same code, so it's so-called anelastic spherical harmonic modeling approach. So they are simulating magnetic field in rapidly rotating solar type stars, and actually they managed to got toroidal field loops that may be resembling what we are seeing in real stars, except that these loops are at the equator of the star, and we tend to find them close to the pole. But maybe a step in the right direction. And there are also simulations by a group in Helsinki, direct numerical simulations in the spherical wedge domain, so it's kind of grid which matches the convection zone of typical star, and this is distribution of the radial velocity, so you see convection pattern here, and this is distribution of horizontal azimuthal magnetic field, and you do see this pattern of systematic rings, which is maybe looking like observations, but this is really going on right now. So the bottom line is that we have no idea how to interpret these maps. And there is a huge gap between theory and observations. And regarding mean field models, I have not seen any mean field models that came close to describing these observations. Okay, so now I will move to, I have half an hour left, right? So now I am moving to a different class of stars, intermediate mass stars. So first I will move from solar type stars upwards in the HR diagram towards more massive stars, and then I return to cooler stars. So these are stars in this mass domain, and these masses correspond to the range between which the stars end their lives as supernovae. So more massive stars is more than 8 solar masses lead to supernova explosions, and the lower limit corresponds to the mass when surface convection zone disappears. So these stars don't have convection zones close to the surface. They have convection in the core. And historically, those stars were the first to be discovered as magnetic, and that was a bit surprising. So that's not the place to have dynamo at all. And what is discovered, what is known about these stars, is that not all of them have magnetic fields, but only 10%. And they have the spectral classes B and AF. They have magnetic fields which seem to be globally organized. And very often, as you will see later, magnetic fields can be roughly described as dipoles which are oblique relative to rotation axis of the star. So something similar to the magnetic field of the Earth, but usually with more inclination. And also magnetic field strengths are actually very, very large. Well, this is the rough lower limit, but it goes up to 34 kilogauss. Also, these stars, those stars which have magnetic fields, are distinguished from non-magnetic stars of the same spectral classes by their unusually slow rotation. So normal A-type stars rotate with periods of 2-3 days maybe, and for these stars, rotation periods of up to some decades have been measured, and for the slowest rotators we have not even seen one full cycle. So there is some extrapolation suggesting that there are a few stars rotating as slowly as 100 years. And there is also correlation between the presence of the field and a certain property that for these types of stars is serving as a proxy of magnetism. So for cool stars, you could say that cool spots are proxies of magnetic fields. And for these stars, intermediate mass stars, inhomogeneous distribution of chemical elements is proxy of the presence of magnetic field. So these stars tend to have very non-unusual chemical composition with overabundances of certain elements like silicon or heavy elements, rare earth elements, europium, and so on. And in addition to that, they have inhomogeneous distribution of these chemical elements. So they have spots, maybe one spot where europium is concentrated on the surface and other spot of iron and so on. And they also have variation of chemical elements with height. So remember, these stars don't have convection. There is nothing really to mix their atmospheres. They have very quiet atmospheres. And this allows them to build this homogeneous distributions of elements. How it is produced, I will mention later. And they exhibit strictly periodic variability. Everything varies. Spectrum varies. Magnetic field observables vary. Photometry of these stars vary. Spectral energy distributions and individual line profiles. But all these parameters, all these observables, change in a very stable fashion with exactly the same period, presumably rotation period of the star. And these stars are easier in that sense because things are stable. You can return to the same star 10 years later and you will guaranteed to have the same surface distribution. So you can accumulate observational data over a much longer time scale than for solar type stars. And what explains the phenomenology of these stars is that they have what is known as a oblique rotator model. So as I mentioned, the idea is that there is a magnetic field which to a first approximation looks like a oblique dipole, and this magnetic field is frozen in the stellar atmosphere. And as the star rotates, we see different sides of this dipole field, and Stokes parameters change, and observables, integral magnetic field observables change. So this is the animation which shows the rotating dipole field, and what you see here is the Stokes V, Stokes I, and here is the mean field modulus, so something that we would infer from the splitting of spectral lines in Stokes I. And here you see the mean line of sight magnetic field, BZ, something that we get from Stokes V, from circular polarization. And in addition to magnetic field, stars have chemical spots, and the second animation shows the effect of chemical spots on the Stokes I line profiles, and the effect is kind of similar to cool spots, except that it's similar in the sense that there is a signature moving across profile, but the signature is opposite. So for solar type stars, cool spot produces a bump, a little emission bump, but for intermediate mass stars with chemical spots, we see deeper. Usually we see deeper lines at the positions of spots, simply because there is more iron or more europium within this spot relative to the surrounding photosphere. A lot of work has been done for these stars, assuming that the field is dipole and modeling integral magnetic observables, these moments of magnetic field, using dipolar field approximation. In fact, it is possible to derive very simple formulas which connect parameters of dipolar field with the average quantities that we measure. So we can measure line of sight, average line of sight field, longitudinal field, and modulus of the field, and they can be related to parameters of the dipole in this way. So what is written here is that BP is the polar strength, so the strength of the dipole. Then U is the linear limb darkening, according to this formula. And then this cosine is the cosine of phase angle. And this phase angle is written like this, where I is the inclination between line of sight and the stellar rotational axis, and beta is the inclination of the magnetic field. So angle between field and the rotational axis of the star. So very simple formulas. You can just measure BZ and then fit BZ variation with these formulas and get out field strength, the inclination of the field, and even the obliquity of the field and inclination angle of the star. And very often one also uses this relation in addition to this formula, so oblique rotator relation. And it's a very simple formula, which is basically saying that there should be some relation between equatorial velocity period of rotation and the radius of the star. Well, the circumference, the equator length should be rotation period times the equatorial speed. So if somehow we know the radius of the star, and we might know that either from interferometry, or we can infer that from model atmosphere analysis, and we know rotational velocity that is measurable directly from line profiles. Period is also known usually. We can deduce sin I. We can deduce inclination angle. So very useful formula. In this case, this numerical factor is written for the situation when we measure period in days, radius in solar radii, and V sin I in kilometers per second. And, well, using this quite simple formula, a lot of work has been done, as I mentioned, and the simplest approach would be to just fit the mean longitudinal field measurements, and this is example of such fits for many stars. So sometimes you see it's very well defined curves with lots of points. Sometimes there is noise and maybe not so many observations as one would wish to have. But nevertheless, a lot of useful information has been obtained from such simple models. And the number of stars, intermediate mass stars, analyzed in this way is maybe a few hundred, maybe 100, 150, 200. Well, first of all, what we can say is to simply plot the stars on theoretical HR diagram, and we see them scattered all over. There is no preference of these stars to a certain evolutionary stage, which immediately tells us that if they acquire magnetic field, that should happen fairly early in their evolution, and then field stays the same, approximately the same. There was a more systematic, more precise, I should say, study where magnetic field strength in stars in clusters was measured. So people measured how strong is the field in clusters of different age, and then they plotted average field strength as a function of age of stars. And then, well, it seems that there is a tendency for the strongest fields to be found in youngest clusters. So there is some change of the surface field strength. It's unclear, however, is this change due to intrinsic evolution of the field, or is this change simply because the star gets larger, and then due to the flux conservation, surface field strength should become smaller. So these two possibilities cannot be distinguished from this paper. And then this is another example of the paper which tried to estimate the incidence, really what is the fraction of stars with this global magnetic field. And, well, it's really not very well defined simply because of this lower cutoff. So what is plotted here is, again, HR diagram, magnetic stars in blue, and this gray background that you see are stars with similar parameters, but without detection of magnetic field. And, well, you can clearly see that depending where you put the cutoff at lower masses, you could have larger or smaller contribution of these gray circles. So this explains the range between 2 and 10%. So if I would only count stars, say, above 2, then it's 10%. But if I include all these lower mass A stars and early F stars, I get down to 2%. And this is for stars in 100% parsecs within the sun, so really in the vicinity of the sun. Then yet another quite interesting observations, which actually came from that paper, from these figures. So this fitting of sinusoid to BZ observations gives us the dipole field strength. So it turns out, very interestingly, that there is a lower cutoff, there is a lower threshold of the dipolar field strength for these intermediate mass stars. As I indicated, a sensitivity of modern spectropolarimetry is sufficient to see, well, few tens of Gauss for these stars, but we are not observing anything below roughly 300 Gauss. So fields below this apparently cannot survive in these stars, and maybe not surprisingly, this is very close to expected equipartition field strength for these stars. So the strength of the field when the average energy of the field is the same as the energy in the gas at the in the photosphere of the star. Yeah. No. So we are sensitive maybe down to 1 Gauss. Yeah. Well, first of all, these two are different studies. So this is just incidence, a statistic study. That there are less stars here, you mean? At the zero mesh? So here. Well, I don't think it's possible to say that the error bars are still fairly large to make these claims. And in particular, what is not really reflected in these error bars is that for the field stars, and these are field stars, so not stars from clusters, but stars from the field, we don't really know their bulk metallicity. So the surface abundances of these stars are very anomalous. They don't reflect chemical composition of the stars inside, in the interior. And these evolutionary tracks, as you understand, they depend on the metallicity. So here they simply assume solar metallicity. So there can be shifts. Well, I don't see that actually here. I think there is a tendency for lack of stars during late evolutionary stages, if anything, like here. It's very, very, very subjective. And again, this is volume limited sample. One could add many more stars. But okay, I think physically this is much more interesting. The minimum dipolar field strength is of the order of equipartition field in these stars. There is an idea, why is that? It's because there is interplay between differential rotation and magnetic field. And these A-type stars that tend to be differential rotating when there is no magnetic field. When magnetic field is present, basically kills differential rotation immediately. And when field is weak enough, it cannot withstand differential rotation, so it's destroyed by differential rotation. But these are kind of hand-wavy explanations suggested in papers, including this one. But again, no detailed models. And maybe the last thing that I want to say today, before continuing with these stars on Friday, right, is that there have been attempts to trace what is happening, to trace the emergence of these fields at early evolutionary stages. So to look at very young A-type stars, so-called Herbig AE stars, so stars with emission lines, but emission related to the presence of circumstellar material. And particularly these studies did that, Alicion and collaborators. And this is a theoretical HR diagram, but evolutionary tracks are now shown for the pre-main sequence evolutionary phase. So stars are moving from here to here, and this is the arrangement sequence. So black points correspond to stars that they observed and did not detect as magnetic, and red points correspond to stars detected as magnetic. And they seem to have magnetic field very similar to what is shown by magnetic A stars. So already these young A stars have well-developed dipolar fields of this strength. And even the incidence is consistent, so roughly 10% show these global fields. So this tells us that whatever is the process by which the stars get this field, this must happen very early in their evolutionary phase, much earlier than the Herbig AE-B phase. Okay, so I like to stop here for today.